Hello one and all, Jake here. Don't mind the haircut, it's only temporary, it'll grow back. But here I'm going to present to you a problem that I encountered in a stochastic processes class. But like 4 semesters before that, I had a theory of probability class that it easily also could have shown up in. It's very basic. And it illustrates something that is pretty important in probability theory. So I wanted to go over it with you guys. So if you can't read my handwriting, I'll just read the problem out loud to you. You deal 8 cards from a standard deck of 52. What is the probability that there is at least 1 card of each suit among the dealt cards? So, for example, here we have a deck of cards, and I'm just going to put the mic down for this. We're going to deal 1, 2, 3, 4, 5, 6, 7, 8 of them. And I'm just gonna hang these up. Alright, so if you look what we have here, we have an ace of spades, we have a 2 of hearts, 3 of diamonds, 4 of clubs. Don't even need to look any farther than that. This deal is already a success. We have at least 1 card of each suit. So pretty much all we're asking is, what is the probability of getting a successful deal like this? And I'm going to give you a moment to just pause and figure it out yourself. Okay, moment's over. Like, you could pause whenever you want. I'm not going to wait in the video. That doesn't really make any sense. So I'm going to erase the board here, and I want you to keep something in mind. The reason card problems are so nice in a introductory probability course, or even beyond that, is because, you know, there's so many different ways you can divide up a deck of cards. If you want to divide them in half, you can go red card versus a black card. If you want to divide them into 13ths, you can go values. If you want to divide them in fourths, you can go by suits, which is what we're doing here. And if you want more exotic fractions, you could even do face cards versus number cards, you know, anything you want. But the key detail about cards that make this all work out is that if you have, you know, n cards and you randomly shuffle them and then you draw one, each of the n cards has exactly the same probability of being chosen. So keep that in mind as we continue to solve this problem. So one approach you might be tempted to try would be to take it step by step and just figure out the probability during each of the 8 cards that you're dealing of staying within the constraints of the problem, of it still being a successful draw. For example, there's a 100% chance on the first draw that you get a card of some suit, and then on the next, there's about a 3 and 4 chance that you get a card of a different suit. And, you know, if you try to do this, I think you very quickly run into a wall. There are way too many branches that you have to consider, and this won't work out. You have to try something else. Now, one very important concept in probability specifically is this idea of complementary probabilities. If I take the probability of an event happening and add the probability of the event not happening, well, that should equal 1. An event either happens or it doesn't. There's no it will kind of happen in between that has a slight chance. It doesn't make any sense. It's either gonna happen or it won't. So if we take the probability of getting a successful deal of 8, which has 1 of each suit, the opposite event would be you get a deal that excludes at least 1 suit. And finding that might actually be easier than finding the probability that it includes all 4. So maybe let's try to run with this idea. Now, what I have in mind here is, let's just take any suit. Let's just say hearts, for instance. I deal 8 cards. What is the probability that I dealt 8 cards and none of them were hearts? All right, we're just doing hearts, but you know, this is interchangeable with all 4 of the suits. Well, let's get some numbers on the board here. My idea here is there are 52 cards in the deck. 39 of them are non-hearts. So how many ways are there to choose 8 non-hearts out of the 52? Well, there are, of course, 39 choose 8 ways to choose 8 cards out of a pool of 39. And the total number of draws that you can have is 52 choose 8. So this is the ones that exclude hearts. This is all of them. And then this would be our fraction. Now, if you're a bit skeptical that that makes sense, let me try to sort of expand it outward and start from scratch in a way that might make a bit more sense. So you deal your first card. What is the probability that it's not a heart? Well, naturally, it's 39 out of 52. Next card. What is the probability that that's not a heart? Well, we just lost one non-heart in the deck, so there's only 38 left, and we also just lost one card in the deck, so there's only 51 left in the whole stack. And if we continue this, 37 out of 50, 36 out of 49. I'm just going to continue on the next line here. We have 35 out of 48, 34 out of 47. It took me a while to subtract 1. It's pretty late at night right now. 33 out of 46. And then lastly, of course, we have 32 out of 45. All right, cool. Is there another way to write this that makes a lot more sense? Well, what we could do is we could say it's 39 factorial. Notice how we're multiplying a bunch of numbers that are counting down. Factorials are a good place to start when we do that. But we do stop at 32. So we're sort of dividing 31 factorial, right? And then that's for all the numerators we're multiplying. For the denominators, we do something similar, where we have 52 factorial, and we're dividing out 44 factorial. Now, what I'm going to do now is just rewrite this exact fraction. So we're going to have 39 factorial divided by 39 minus 8 factorial. Hopefully you agree that I can do this. 31 is 39 minus 8 after all. And then we're going to multiply instead of dividing. That means we would have to flip this fraction over. So then we get 52 minus 8 factorial divided by 52 factorial. All right, neat. So what next? Well, what we're going to do is we're going to multiply this whole thing by 8 factorial over 8 factorial. Yeah, if this doesn't make sense, trust me, it will in just a second. So what we will have here is we're going to sort of just multiply this 8 factorial into this denominator and multiply this 8 factorial into this numerator. So what we're going to end up with is 39 factorial divided by 39 minus 8 factorial times 8 factorial times 52 minus 8 factorial. That is not where I wanted to put the factorial, my bad. Times 8 factorial divided by 52 factorial. And if you notice, this is none other than the definition of 39 choose 8. And then this is 52 choose 8, except reciprocated. So it's 1 divided by 52 choose 8. And this is indeed the fraction that we got at the beginning. 39 choose 8 over 52 choose 8. By the way, if you have no idea what I'm talking about with all this choose nonsense, right there is a link to a video I did a little while back explaining exactly what that means. So all of this was just a way to sort of confirm the idea we had earlier that 39 choose 8 over 52 choose 8 was the probability that we end up excluding hearts in our deal of 8. The problem is that this is just hearts. There are 4 suits. So what do we do now? Well, the probability of excluding clubs is analogous. I mean, there's going to be the same exact numbers you're working with. So that's also going to be 39 choose 8 over 52 choose 8. Same thing with diamonds and spades. So if I want the probability of any of these suits being excluded, well then wouldn't I just add up the probability of each one being excluded, right? So then we would have plus 39 choose 8, 52 choose 8, plus ... And then, combining like terms, we would just get 4 times 39 choose 8 divided by 52 choose 8. Didn't mean to draw that fraction bar there. All right, so this would be our answer, except there's a bit of a problem. What's the issue? Well, I'm going to make another pass at dealing 8 cards, and we're just going to see what happens. So we have 1, 2, 3, 4, 5, 6, 7, 8 from a freshly shuffled deck. All right, cool. By the way, full disclosure, I'm not actually shuffling these decks each time. I'm doing this to illustrate something. So let's just take a look at what we have here. We have spades, we have hearts, and that's about it. So we're missing diamonds, we're missing clubs. That means we're missing 2 suits. Now, the question I have for you is, using this method where we count up the 39 choose 8 ways there were to exclude one suit and then 39 choose 8 ways there were to exclude the next suit, how many times do we count this? Right? It should be 1, right? Ideally, we want 1 because there's only one way to deal these 8 cards exactly. But we actually counted them twice. Once when we were excluding diamonds and once when we were excluding clubs. So what's a guy to do in this situation? Well, what if we took all the possible ways to exclude 2 and we calculated the probability that we encounter one of those ways and then just subtract it out, right? Because we've counted it twice. We want to only count it once. So if we take all of the ways there are to exclude 2 suits and subtract that number out, then what we're left with is just each of these deals only being counted 1 time. So hopefully, if that makes sense, we can proceed. All right, so I've just pushed these down so they're out of the way, but I'm keeping them on the board so that we know we're dealing with 2 suits being excluded. All right, just a little reminder. So what is the probability of 2 suits being excluded? Well, let's just take 2 particular suits, say clubs and diamonds, and sort of put them in our head as excluded. So we're not going to, any draw that includes one of these 2 suits, we're going to avoid counting. What's the probability that we get a draw that we're considering successful in this case? Intuition might say, well, there are 26 cards, and then you're choosing 8 of them. There are 26 cards that aren't a member of one of those two suits, right? And then, of course, there are 52 choose 8 ways to, draw the cards in general. So, hey, pretty much the same as what we had earlier. But just to confirm, I'm going to do it fraction by fraction, just like I did before. So, first card, 26 out of 52. Probability of excluding both diamonds and clubs. Next one, 25 out of 51. And this will continue 8 times. So let me just speed it up here. Okay, there we go. Why is that a 9? I meant that to be a 5. All right, here's the multiplied out fraction, and we're just going to simplify it as we did before. So we got 26 factorial divided by 26 minus 8 factorial. This is 18, and we stop at 19, so that makes sense. And then we got, this should be times 52 minus 8 factorial over 52 factorial. And I imagine I don't need to go through these steps again. You understand that this can be simplified to 26 choose 8 divided by 52 choose 8, just as we intuited earlier. So now here's a fun question. We subtract this out how many times exactly? Well, let's think about it like this. We have 2 suits that we chose to exclude. In this case, it would be diamonds and clubs, but any choice of 2 suits will do. How many ways are there to select 2 suits to exclude? Well, there are 4 of them, and we choose 2. It's 4 choose 2. So what we're now going to do is we're going to take our initial 4 times 39 choose 8 divided by 52 choose 8. And we're going to subtract out 4 choose 2 times 26 choose 8 over 52 choose 8. All right, cool. Does this now answer our question? So we had all the ways there were to exclude 1 suit, and we're subtracting out all the ways there are to exclude 2 suits at the same time. Because those would have been counted twice, we're going to subtract them out once, and then there's only going to be 1 left. This should work, right? There's another problem. And of course, to illustrate the problem, I'm going to, one more time, deal 8 more cards from my randomly shuffled deck, and we'll see what we get. So, I'm going to put this here. All right. We got 1, 2, 3, 4, 5, 6, 7, 8. Cool. And we're going to hang these up, see what we get. And would you look at that? A royal straight flush. But, how many times did we count this? So let's take this from the top. When we were excluding 1 suit at a time, we counted this once for excluding hearts, once for excluding clubs, and once for excluding diamonds. So we counted it 3 times. Then, when we moved on to excluding 2 suits at a time, we subtracted it out once for diamonds and clubs, once for diamonds and hearts, and then once for hearts and clubs. So we subtracted it out 3 times as well. So in order to properly count it, we're currently at 0. We counted it 3 times and we uncounted it 3 times. We need to recount it 1 more time. So now all we're questioning is, what is the probability of excluding 3 suits in our deal of 8 cards? Well, I shouldn't have to go through the details of explaining to you why 13, choose 8, divided by 52, choose 8 is an answer that makes perfect sense. If you want, as an exercise, you can go through the multiplication method with all the fractions, but we're going to leave that here. There are 13 cards in the deck that are of one suit that we're not excluding, and then there are 52 in the deck in general, so this makes total sense. And then we're left with the question of how many times are we adding this term back in? We're doing it once for excluding, for instance, clubs, diamonds, and hearts, but how many different ways are there to choose 3 suits to exclude? Well, there's actually 4 choose 3. So, that's pretty simple. And while we're at it, let's also note that this 4 was actually a 4 choose 1 in disguise this entire time. We just didn't realize it until we continued the pattern a bit more. All right, cool. So now, does this answer our question? No. But it's not because the pattern continues and there's a way to exclude 4 suits. Obviously, you need to include at least 1 suit, or else you have no cards in your draw of 8 cards. That wouldn't make any sense. But remember, this is the probability of excluding at least 1 suit. The initial question was, what's the probability that all the suits are included? All right, so now I've cleared the board here, and we're going to write our final expression from the beginning. So what we have now is 1, the probability that anything happens. We're going to subtract out the total probability that at least 1 suit is excluded. Now, if we do a little combining of like terms here, everything that we had on the board earlier actually had the denominator 52 choose 8. And now in the numerator here, we're going to have what we got from excluding 1 suit at a time. And then we subtracted out the 4 choose 2 times 26 choose 8 ways to exclude 2 suits. And adding back in the 4 choose 3 times 13 choose 8 ways to exclude 3 suits. And if you want to go even a step further, we can make this 52 choose 8 minus 4 choose 1 times 39 choose 8 plus 4 choose 2 times 26 choose 8 minus 4 choose 3 times 13 choose 8. We're reversing the signs here because we're subtracting these positives and subtracting this negative, so it becomes a positive. All over 52 choose 8. Let me make sure this is a binomial coefficient. And voila, this is actually our final answer. So this expression here is the probability that all of the suits are included in a deal of 8 random cards from a deck of 52. And if you actually calc this out, you'll see that it's just under 69%, I believe. And this answer kind of makes a little bit of sense. I mean, it would seem like you would usually get all 4 suits, but you would not get all 4 suits enough times where it's not completely a negligible percentage. And I think this number captures it pretty well. Hello one and all, and welcome to Jake at his computer, everyone's favorite segment of the show where I compute things. Now here in Wolfram Alpha, I've typed in that expression that we got on the board earlier. I wasn't going to show me typing it in. That would just be a big waste of time because this takes a while to type. But here we could see the expression in all of its Wolfram Alpha glory, and we actually get an exact fractional result. But what's more useful to you as a human probably is this decimal approximation. We can see that's 0.68542 and so on. or a little under 69%, which is what I said earlier. Now let's just close out of this. Oh, what on earth do we have here? It's not a C program this time. It is an R program. R is a statistical software package that lets you do a lot of interesting things. I like it for doing probability and stat stuff, and sometimes other numerical things as well. And let me just take you through how this works a little bit. So here I've set up my cards array. It's 13 zeros, 13 ones, 13 twos, 13 threes. We're representing each suit as a different number, and all that matters is that the suit is there. It doesn't really matter that they're all different values or whatever. This is a good simulation for our deck. Now here we have this stats array, which is just 16 zeros. I'm going to get back to what that is for in a second. So now we have for I in 1 to a million. It's going to iterate from 1 to a million and do something a million times. Now the big thing about probabilities is that you really can't prove them per se. I mean, you could prove them like I did on the board and demonstrate why the probability you got is the correct answer, but no matter how many times you run an experiment, you can't actually prove conclusively that the result you get is actually reflective of the actual probability of the event. It's always going to be possible that through some cosmic accident, you got very coincidental results, and your probability actually isn't accurate. But what computers let us do is run things a lot of times, dealing cards and shuffling them into the deck, and then dealing them again, and then tallying it down. It adds up to a lot of time, so to do anything even remotely convincing, we have to speed it up using a program like this. So each iteration, what it does is it samples 8 cards randomly, and here we have 4 initial flags for the 4 suits. They're all initially set to 0, and then it goes through the sample it took, and for each card, it checks the suit and it marks off that suit as present. It changes it to 1. Now, we have this magic number. What is this? It takes the presence of each suit as a binary digit, and it basically calculates the number that you would get from that binary number plus 1. And the reason I add 1 is because in R, indexing starts at 1 and not 0, so R sucks for that reason, but whatever, not a big deal. So then we take our stats array, which is initially all zeros, and we have our number, which represents the state we just got, which suits are present in our deal of 8, and it adds 1 to it, and then it just prints the results. All right, so that's basically how it works. And let's just, we actually have to copy this, and let's open R up and just paste the whole program in. And it's going to stop for a second. We are doing this a million times. We should be expecting about 685,000 successes. And if we just give this a moment, it'll come up with the stats. Please wait. There we go. Now, wow, look at that. 685,903 successes. If I run this again, it's going to be a slightly different number, but it's going to be within the same ballpark. And that's all we really need to confirm our suspicions of what the probability is. We already have like a proof of the actual exact number that we got earlier, but we're just trying to sort of confirm-ish it using an actual experiment. So that's what this number is. Now we can actually go and see some more detailed statistics. For example, so there were 0 instances where all 4 suits were excluded. That shouldn't surprise anyone. But we have this 2, this 4, this 2, and this 1. These were counting the number of times where only 1 suit was included in the 8 cards. And as you can see, this doesn't happen very often. I was running this program earlier, and then 3 of them were 1s, and then 1 of them was 0. So this is actually on the maybe high side of it happening. Then we have slightly bigger numbers in the 2000s range that represent 2 of the suits being included. And then the big ones is 3 of the suits being included, only 1 being excluded. And that's these 4 numbers. And of course our successes is this last number. All of the suits would be set to 1, and then the binary number corresponding to that is 15 plus 1. So yeah, at this index is our successes. And how cracked am I at R for figuring out how to do this in such an elegant way? So this has been Jake at his computer, and we're going to go back to the whiteboard real quick. All right, so we've headed back to the whiteboard, but I have nothing else to show you this time around. I'm not going to waste any more of your time. I just want to say thanks for watching. Leave feedback in the comments. Let me know if there are any math topics you want me to cover. I mean, I'm willing to, kowtow to the demands of the viewers if they so desire. And as usual, stay awesome, have a good night, and good luck in the future. Subscribe, like the video, comment, just interact with the video in some way. Lets me know that I'm not talking to the wall, that you guys are enjoying it. Yow.